The Edge AI Lifecycle is the steps you take to plan, implement, and monitor an Edge AI project. It generally follows the same process as any engineering project, but with the added complexity of dealing with data. Before starting the project, you need to very clearly define your problem statement. Let's say you are designing a slick new earbud that automatically adjusts the outside volume depending on the user's desired preferences. This requires some complex engineering to do active noise canceling. However, active noise cancellation is easily done with classic signal processing and does not require any AI. As a result, it's important for you to consider your requirements carefully and ask the question if AI is even needed. Sometimes more traditional methods will accomplish your goals with less effort and less complexity. However, let's say you then want your earbud to respond to a particular keyword or phrase. As it turns out, that is a much more difficult problem, and one where AI actually helps. Now that you have identified where Edge AI can help, let's look at the steps you would likely take to tackle such an effort. Edge AI projects look like just about any engineering or software undertaking. As with any project management task, you should define your scope, which includes the stakeholder requirements and deliverables. It also takes into account things like the user interface and any necessary support. To meet this scope, you often need to consider the amount of time and money you have available. Since we're talking about Edge AI, you should think about the need for some sort of connection in your devices. Do you need to remotely collect data, send notifications, or apply updates to your devices? If so, you will need to connect your device to the internet, a local network, or another device, like a user's phone. This also includes weighing the trade-offs in latency and bandwidth. Edge AI helps reduce latency and bandwidth, but maybe you need to use more powerful AI in the cloud. Finally, energy usage can play a big role, especially for battery-powered devices. Consider the trade-off between on-device compute and transmitting the data to another location for processing. Connectivity and energy usage are part of the project scope, but I wanted to mention them specifically when dealing with Edge AI. With those constraints in mind, let's look at a typical Edge AI project workflow. Once you have identified the need, you will want to flesh out the requirements and define the project scope. Such needs can obviously evolve, but starting with a clear goal is helpful. To start, you will want to collect some initial data that includes information about the problem you're trying to solve. From there, you will analyze that data to look for trends to extract that information. This can be a complex task, and it's where data scientists and domain experts become indispensable, as they often have the training and knowledge about how to collect and analyze data to provide good insights. In most cases, you will find that you spend the vast majority of your time collecting, labeling, and analyzing data, rather than on the actual task of building and training machine learning models. So it's important to get this part right so you don't waste a lot of time. Let's look at a hypothetical example project. Imagine you are in charge of maintaining public escalators across a city. Repairs can be costly and cause delays for pedestrians. Rather than wait for something to break down, you decide to use Edge AI to help predict when one of your complex moving stairs machines needs maintenance. This might be based on a real-life example. In 2021, the Prague Public Transit Company worked with the tech firm Neuron Soundware to extend the life of the city's metro escalators by using Edge AI sensors. After defining the scope of the project, you and your team decide to install low-cost IoT sensors on every escalator in the city. You discover that the escalators vibrate in odd ways when they are about to break, and as a result, you plan to collect motion data with accelerometers built into the IoT devices. The low-cost IoT sensors you identified are powerful enough that they can perform anomaly detection on the devices themselves. So an Edge AI solution is a perfect fit for this problem. In many cases, raw data often has fields missing or out of place. Some samples might be mislabeled, so it often helps to clean the data, which refers to fixing or removing incorrect or corrupted samples as well as dealing with duplicate entries. There's a saying in computer science that goes garbage in, garbage out. It refers to the idea that poor quality or biased information used as input to a system will usually result in similarly poor quality output. So if we use poor quality data to train a machine learning model, the model itself will also likely be poor quality. That's why we spend time cleaning the raw data. Additionally, the data, even if cleaned, might not be good enough to train a robust model. As a result, we can often perform feature engineering to help us out. Feature engineering is the process of transforming the raw data into other values that better represent the underlying information that's needed by the machine learning models in order to make accurate predictions. This might include figuring out which values or axes provide the best information and dropping the rest. Or maybe it involves transforming the data in some way to identify patterns. For example, converting time series data, like the values we might get off the accelerometer, into its frequency components might offer better insights than the raw values alone. In fact, looking at the frequency information like this is often a good way to go when dealing with vibration data. Choosing the best features requires time, experimentation, and a good deal of knowledge about the problem domain. Even though the computational power required to extract these features is often non-trivial, it will save you in the long run, as it usually means smaller and more efficient machine learning models. At this point, you are ready to train a model. This is just a set of math operations that attempts to identify patterns and make some kind of prediction. In our case, it will take in accelerometer data and predict if the escalator is running normally or not. To train the model, we use one of the many possible machine learning training algorithms. The values in the model will automatically be updated to make better predictions. From there, we want to test our model. At first, this might include using some data that we put aside that the model has never seen. We can use this method of validation to tweak our data cleaning, feature engineering, and model as needed to get better accuracy. Once we have a model that we are happy with, we can build a physical prototype and test it in the field. This usually includes deploying the model to one or a few edge devices for testing. In my experience, just because a model performed well on test data does not mean it will perform well in the field. So it's worth testing in the environment where you plan to ultimately deploy your devices. So let's say I build a test application around my machine learning model and load it onto a development board, like this one. We attach the device to a few escalators and let them run. Or maybe we induce a few errors to see if our device notices. In our hypothetical example, let's say that we start seeing too many false positives and negatives in the field. The device is simply missing too many anomalies or falsely reporting them. So we have to revise the plan. After some brainstorming and research, we decide to capture audio as well as electrical current used to power the escalator. Often, mixing data from different sensors can give greater insights than just one sensor alone. This is known as sensor fusion. When it comes to edge AI projects, I usually find a way to collect data and create a prototype as quickly as possible, often in only a few days. This helps me understand if I'm on the right track before investing additional time collecting data to make the model more robust. In the machine learning world, this entire process of collecting data, cleaning it, extracting features, training a model, testing the model, and deploying it is known as a machine learning pipeline. It is often possible to automate this entire process, which is one of the elements of machine learning operations, or MLOps. We will refer to this combination of feature extraction and model inference as an impulse. In the majority of edge AI cases, the impulse is what gets deployed to the end device rather than the full pipeline. After some testing, let's say that our team is happy with the performance of the prototype, which performs sensor fusion and anomaly detection on the combination of vibration, audio, and electrical power usage. At this point, we are ready to move into full production. But before doing so, we need to collect more data in order to create a robust model that works well with every escalator installation. Let's examine some pitfalls when it comes to data collection. While it's not AI, this viral video in 2017 demonstrates how technology can easily have bias built in. The soap dispenser only worked with lighter skin tones. From this, we learned that we should test our devices with a diverse set of users and in various environments. This holds especially true with machine learning, where the internal workings of many models are often too complex for us to fully understand. That means we rely on training data to teach the model how to operate. AI simply learns from the data you provide it. So if you give it biased data, the model will simply reflect that bias. When it comes to collecting data, make sure that you think about all the possible use cases for your Edge AI application, especially if it is designed to be used by people. Make sure you take age, race, gender, and disabilities into account. In addition to bias, operating environments also play a big role. One of the big reasons for Uber's fatal self-driving car accident in 2018 was that the AI system had difficulty identifying someone walking their bicycle across the street at night. Environments can change. Just because we collected initial data from, say, a short escalator running in the summertime does not mean a model trained on that data will work for a long escalator running in the winter. We also need to make sure the data reflects the different load levels, as vibration, noise, and energy usage will be different from when no one is on the escalator to when it is full of people. We can either collect data to make a single robust model for every situation, or we can train a model for each individual escalator. To make this example easier, let's say we decide to create one robust model for all escalators in all environments. We would follow this procedure again to train our robust model on the cleaned production data. Then we would deploy to all of our devices. Finally, we would want to monitor and maintain the Edge AI devices. This is part of the operations and maintenance activities necessary to keep equipment and software running for its entire lifecycle. If we find that the model is no longer working, then we would go back to square one to collect and analyze data. Remember that the model does not exist in a vacuum. It is often built into a larger application. As a result, Edge AI should be treated like any software or machine learning project where you employ best practices in development and maintenance. This might mean using continuous integration and continuous delivery processes, as well as device monitoring to determine when updates are required. Understanding the entire Edge AI lifecycle of identifying the use case, collecting data, training a model, and deploying your application will help you tackle unique engineering problems. Next time, we will see how this lifecycle can be automated in a process known as Edge Machine Learning Operations, or Edge MLOps.